Okay, so we're very pleased to have David Polarski, and he's going to tell us about the growth index of perturbations, formalism, there's a slight typo, and exact results. Okay, take it away, David.
Oh yes, it's not a formally.
The formula, yes. It's okay.
Yeah. And I choose my word, right? When to make the where to make the mistake.
Oh, it's not a typo.
It is a typo.
Okay, I'll let you go. Go.
Okay, so first of all, I would like to thank the organizers, first for the invitation to give this talk, but also for this opportunity. All my colleagues and all my collaborators, they know that I like to work during night. It was always my dream to deliver a talk during night. Now, finally, I fulfill my dream and I do it today. I had to wait the end of my career, but okay, here it is. So you see, this is the time here. So I will talk about the growth index. So it was originally introduced by Peebles, okay, in 1984 for the characterization of growth of perturbations in open universes. So here, and he found that gamma, the growth index, is close to 0.6. Now, this is quite old. Interest was revived in the assessment of dark energy models and modified gravity in general. Now, in lambda CDM and many smooth dark energy models, inside GR, you have gamma 0.55. So you see, this is the transition in 35 years, but actually it has a lot of information in it. And moreover, as you will see, there are models where you can depart very strongly even from that value. So let me just remind you a few things about the growth index. So matter perturbations can be characterized by the growth function. Okay. Now, for some reason, I have something on my screen. But matter perturbations can be characterized by the growth function. Okay, here is the definition. Okay, it's this. This is the equation. And I put here a G when I will consider modified gravity theories. Of course, in general relativity, this is just one. Okay, here is the definition of the growth index. It's just that this growth function here, you write it in this way. And in general relativity, of course, there is no dependence on K because the growth does not depend on scale, but it will depend on Z, okay? So even what you find on the first slide is just an approximation, okay? For example, when you say that it's constant, it's an approximation. In lambda CDM, gamma is close to 0.55, and it is really quasi-constant in the past, but only in the past, certainly not in the future. And it can be very different from that value in modified gravity theories, even today, okay? Or around today, I mean. I wanted to say one more thing here. No, I will keep it for later. Okay, these are all things that you know, and you know, this is a figure from an old article that I did long ago with my student, by then my student, Radwan Ganuji, where we just took this equation, okay, you take this equation, okay, you choose a value of omega m naught, and you choose a value of WDE today, and then you can, it is very easy to show that there is a constraint in the plane gamma naught and gamma prime naught, where gamma prime naught is the derivative of gamma with respect to Z today. So the 0, as usual, is for today. The prime is for DDZ. And you see, all those values are allowed. All those values are allowed, okay? Whenever you are on the line, they are allowed. And in practice, when you look for particular models and what happens with perturbations, they choose these values, okay? And you will understand better in this talk why you don't have the other values, actually. You see, it's very amusing that, by the way, it's almost horizontal. So the slope is not zero. So it's not constant, certainly, because the slope is not zero. So it's certainly not constant. But the slope is small and small negative. So you see all those methods, they're almost at the same height. Okay. So let us start with exact results in GR. Let us start with exact results in GR. When gamma is constant. So now I assume that gamma is constant. Okay. All background quantities can then be given in parametric form. So you can show, okay, it's not so, well, after some work, that all the quantities, the background quantities, A, T, H, Z, and so on, whatever background quantity you want, they can all be expressed in parametric form as a function of omega m. In particular, the equation of state of dark energy. So here is the formula. So you see, it depends on omega m. So I insist that this is for constant gamma, okay? Do you see my screen properly?
Yep, we do.
Okay, fine. So in the asymptotic future, so first let us see what it tells us. It tells us the following. In the asymptotic future, omega m goes to 0. Okay, so I will call W infinity the value, the asymptotic value of W in the future. It's this, clearly, very clearly. And you see that gamma is allowed between 0.5 and 1. Why is it smaller than 1? Because this means that the W infinity is smaller than 1 minus 1/3. So we still get asymptotically an accelerated expansion. And bigger than 0.5, because at 0.5, it will diverge. In the past, so in the past, of course, a genuine dark energy will disappear. So omega m goes to 1. Okay. What is the W in the past? W in the past is between 0.5 and 0.6. Again, here it will diverge, okay? In this range, it will not diverge. So why is it now 0.6? Because smaller than 0.6 means that this is smaller than 0. So really, you don't spoil the matter domination, okay? It will disappear in the past. So you see, between 0.5 and 1, between 0.5 and 0.6. Okay, this is just to show you that if you have a exactly constant gamma in the past, you see that getting those values of W today, okay, gives you approximately these values. I think this was done for 0.3. This will, of course, depend on omega m naught. But you see, these are the values that you expect for a constant gamma in the past in GR. Okay, what are further consequences? They are the following. I told you that in the past, gamma can go from 0.5 to 1, but actually, in this range, in this interval, actually, a part of the interval between 0.5 and 6/11 will give phantom behavior in the past. So you have to take that into account if you have models that cannot do that, like quintessence. And in the future, well, in the future, gamma, when it lies between 0.5 and 2/3, will give phantom behavior. So you see, from everything what I told you, in the past, it had to be between 0.5 and 0.6. In the future, all this range gives phantom behavior. So it is perfectly clear the dark energy dominated universe, that deep in the dark energy dominated universe, phantom regime is unavoidable. Because that interval allowed in the past is exactly inside the interval that will give you phantom behavior in the future.
Sorry, David, can I ask a question at this point?
Yes,
is this the end of physics in the past and the future? If, I mean, essentially this seems to, I mean, tell you that you're not in the effective field theory regime.
Okay.
Is this something you worry about? Like the null energy condition is violated, yada, yada.
Well, I will answer you in the following way. I think in the past, it's not so, I'm not, well, when are you actually worried? In the past or in the future?
No, just in general, like, I guess like various people would like to have a good effective field theory description, maybe.
Yes, but you see.
I mean, okay, if we believe we can do quantum gravity, then you would believe that basically we could put together a theory that would work everywhere.
Yeah, but then for quantum gravity, you don't expect it to happen at the beginning of the matter-dominated stage. Okay. I guess you have to go much further. This only means that you will have to, but this is not important for us.
Okay, thanks.
Okay? So, but I understand your question. So it is more or less in the past that you should worry, but in the far past, I don't have to go that far. And what I wanted to say is that, you know, usually when you say asymptotic, mathematically, you have to go to infinity, you know? But in physics, it's not like that, okay? Very often, when you say that something tends to a limit, it tends to it, you don't have to wait infinite time. This is my point. And we will see an example with GDP, okay? So, just a few numbers. Gamma equal 0.6 means that W at minus, so I will keep saying minus infinity, okay? Which means the asymptotic path in the matter stage. It's 0. The celebrated 6/11, when gamma is constant, okay, is exactly the gamma for which W minus infinity is -1. So if you look at this equation here, this equation, okay, what is the gamma that gives you -1? So it's 6/11. And gamma 2/3, as we said here, okay, is the value for which W in the asymptotic future gives -1. Okay. So, what are the models that can realize a constant gamma? Certainly not quintessence, because it cannot enter the, and by quintessence, I mean the minimally coupled scalar field, of course, and the old quintessence, say, because it cannot have a phantom regime. But as we will see, there is an interesting way to circumvent this no-go theorem. And it's the following. If you have tracking dark energy, in other words, gamma at -infinity will be some value that is not equal to 1. And in order to fulfill that, you need to find a couple of gamma m and gamma that are a root of this. And actually, as it is the root of f, for omega m smaller than 1, this is not 0, so it's actually a root. I will keep saying in this talk a root of f, but actually it's a root of this. Yes, there was a question? Okay, so just interrupt me when there is a question. And actually, you can see very nicely with this diagram what happens. I think this is a plot of the value of W for 0.61, for gamma equals 0.61. And you see, it starts from this value, okay. And it comes here. So for gamma equals 0.61, what will happen is that omega matter will tend to this value just because W of dark energy, okay? Because W of dark energy will tend to 0. This is why we have tracking dark energy. So then the values of omega m and omega d, they will freeze in the past. And this is how you can circumvent the no-go theorem. Okay. Now, let us look. So you have clearly an infinite number of roots. So I give you now 0.61, but any value bigger than 0.6 will intersect omega m at one of these points. So you have an infinite number of roots, okay, for gamma between 0.6 and 1. So let us look at particular cases where this is done. First, we take gamma, which is very close to 0.6. So this means that I consider now models that will intersect here, very close to 1. And indeed, you see, epsilon is just 1 minus omega minus infinity, okay? So it's much smaller than 1, okay? So actually, epsilon is nothing else than omega DE. This is the point, huh? Epsilon is omega D in that case. There will still remain a very small fraction of omega D. Now, from observations, this is allowed. Because observations tell us that epsilon should be very small. But on the other hand, as you see, those gamma are larger than 0.6, but they are not sufficiently large. I remember that it should be larger than 6/11 to avoid phantomness. No, sorry. I missed now the arguments. No, it's in the future that you get the problem. Remember, in the future, when gamma is smaller than 2/3, it's phantom in the future. In the past, it's okay, because the phantomness was between when it's smaller than 0.5454 6/11. So actually, this value, which is larger than 0.6, is okay in the past, but not in the future. So it's okay with observations, but it's not okay with the future. Now, can we avoid W infinity in the phantom regime? Yes, but then omega in the past is too small. For example, if we take 2/3, then in the past, it's 1/8. Clearly, deep in the matter, well, it's not even a matter era, okay? It's not even a matter era. No, sorry. It is a matter era, but it's changed. This is the way I should take it. Because now, so this is omega DE, we agree. This is omega M. And you see omega M, I am a bit confused now. Yeah, this is omega D. No, I was wrong when I said that this is omega DE. This is, sorry, no, I'm confused. No, I'm confused, sorry guys. Okay, it's also the first talk at night. So it's omega M. Yeah, so clearly this is omega M. Yeah, of course. This is omega M. Okay, so now it's completely clear. I was correct. This is omega DE, and this is omega M. And here you see that if you want to avoid that the equation of state of dark energy in the future is not phantom. So you want to avoid that. You need a gamma larger than 2/3. So this is not the case here. So here it's okay from the observations, but it's 0.6 something. Clearly it's smaller than 2/3. It will be phantom in the future. So if you want to avoid that, you can do that, but then gamma is larger than 2/3. And then you see here, omega M is clearly completely ruled out. And it's exactly what I said. There is no matter stage, okay? And you can even find the gamma where the matter stage almost disappears. So, in conclusion, constant gamma is ruled out for quintessence, but it's also ruled out for WDE. And by this, I mean for a genuine dark energy component, because the only way that it's not ruled out is when it's 0. And this is, of course, not dark energy. Okay. It is very surprising that what appears to be a tracking solution, okay, actually appears also in the following system. I consider dark energy plus dust plus unclustered dust-like component. So omega dark energy is 1 minus omega M total. Omega M is almost all of omega matter total. So by omega matter total, I mean, of course, unclustered dust-like matter plus dust-like matter, okay? And the unclustered dust-like component is the X component, okay? I call it epsilon times omega M tot. So this is a small parameter in the problem. So this is quite clear. Now, you put this in your equation for the growth of perturbation. You write it as a dynamical equation for gamma. For this system, you solve it in the limit when omega M tot goes to 1, and you end up with this result. So you recognize here the first two terms that were here. okay? That were given here. Of course, the reason is that this value, you can show, it's beautifully simple to show, that the asymptotic, for this system, the asymptotic value of gamma in the past is given by a root of f, and therefore, it is this expansion which you can continue, of course, and you recognize the first two terms that were given before. But there is a kind of small mystery here. First of all, you notice that this does not depend, it's completely independent of W dark energy. You would expect that this result would depend on the equation of state of dark energy in the asymptotic past. But no, it has completely disappeared. And you can actually summarize this in the following way. If you take the solution of the equation for gamma, for non-vanishing epsilon, you take the limit of this solution for omega tot going to 1. And then you take the limit when epsilon goes to 0. You end up with 3/5, of course, because this is the solution here. This solution here is here. And the limit when epsilon goes to 0 is 3/5. But imagine you do something else. You take in reverse order the limits. So you take first the limit when epsilon goes to 0. So epsilon, you put epsilon equal to 0. And then you take the limit when gamma goes to 1. Well, then, of course, you will end up with gamma minus infinity, which is just given as a function of W minus infinity through this equation, or through this equation, okay? Now, why is it so? Because you can show, and I will explain it to you a bit later, that when gamma is a dynamical quantity, the solution gives in the asymptotic past, but also in the future, I will discuss it in details, the same relation with the W minus infinity as in the constant gamma case. So to summarize, I take the limit when epsilon goes to 0 of this, it's 3/5. And if I take immediately epsilon equals 0, which means that there is no x component, I get the usual result, gamma minus infinity. And the two are not the same. So we were a little bit perturbed when we saw that result. We didn't quite understand. I must say I didn't, from the beginning on, I was very intrigued. I had to check my calculations many times to make sure that indeed this root of f was the limit of this. But you know, you can show it, you can look it in our paper. By the way, this is contained in a paper with my collaborators, Didier Felbach, my present student Rodrigo Calderon, Radwan Ganouji, and Alexei Starobinsky. So I was actually very surprised with this result. I had to check it several times. And then I thought, I put it even the calculation aside for some time. And then I came back to it. And then I realized, yes, it's really like that, okay? If you solve for the equation, you end up with something which does not depend on W minus infinity, and which actually is the root of f. And when we came back to the problem and we did it thoroughly, we understand a bit better. I cannot claim that we understand very well, but a bit better. At least this confirms how this is possible, how this inequality is possible. Why is it that you cannot invert the limits? This is my point. How come that you cannot invert the limits? Epsilon going to 0 and omega m goes to 1. So you make an expansion of the solution, okay, around omega m dot equal 1 and around epsilon equals 0. So this epsilon close to 0, this omega m dot close to 1. Then you can show that you get the following. You see, I give you only the first, terms in the expansion, and I'm sure you trust those numbers, and you see what happens. I can indeed take the limit when epsilon goes to 0, because this is of order epsilon. So these are all these terms, okay? When you take epsilon going to 0, this disappears. But you see, you have poles. In other words, you cannot take the limit. You cannot take this limit. Or you take first the limit. First, you take the limit when omega m dot goes to 1. Okay. Then this term disappears and this term disappears. After that, you can take the limit when epsilon goes to 0 and you get 3/5. This is correct. But if you start by taking first the limit when epsilon goes to 0, this is not possible. Okay? And this just explains why you cannot just put. So if you put by hand from the beginning epsilon equals 0, you hand to the regular solution and you just don't end here. So this is very strange. This is a very strange result, but this explains why those two do not commute. At least mathematically, it explains it. Okay. I want to say here a few things about a constant WDE beyond GR, because you see, let us assume that gamma is constant, okay? Can we have a WDE constant beyond GR? Well, beyond GR, in principle, it's possible. And the reason is very simple. The reason is that we have this additional freedom, which is the G. And you can just show that G should be equal to this quantity. So if you ask WD to be constant during all the expansion, G has to be this quantity. If you ask something weaker, but maybe more reasonable, that WDE is constant during part of the expansion, then you end up with this requirement. But anyway, in all cases, it's strongly violated in many modified gravity models. And my point is to explain you why, okay, without going into details. If I take a mass scalar tensor model, I know that G effective today should be 1. Okay, this is actually today will be very large. It's a theory, it's massless scalar tensor. So there is no screening. So the only way to get the right G effective is to have a very large omega Bronsdicke. Actually, it comes from the solar system constraints. Omega Bronsdicke is very large because the post-Newtonian parameter gamma is so close to 1. But as a consequence, because it's very large, bigger than 40,000, this disappears, and G effective today, okay, G effective today is this number, which is G, okay? It's the only way, it's the only way that G effective today is G. In other words, G naught is 1. Okay, G naught is G effective divided by G today. Okay, so in Marcel's scalar tensor theory, the G effective, I will say it more precisely, the G effective that appears in the growth of perturbations okay, the G effective that appears here in the growth of perturbations is the G effective which plays the role of Newton's constant also in the attraction between two test masses. So today, it must be equal to Newton's constant. So today divided by G, it must be 1. Now, if you look what I said here, you must remember that omega m, or even here, you must remember that omega m today is much smaller than 1, so it's impossible to fulfill it. And for FR models, it's again the G that gives the problem, because it's very easy to see that a viable FR model will always have a G effective bigger than 1. In other words, G is even worse. It will be bigger or equal to 1 for all Z and all K. So for those two models, it is quite clear that you cannot have a constant WDE, because you cannot satisfy neither this equation nor this. This leaves, of course, open the possibility that I will not discuss here to realize a constant WDE, but for G smaller than 1, but certainly not in these models. Now, let me say a few words concerning the true evolution inside GR. So this is this evolution. So this is this equation, okay? And actually, this is the equation that I solved here, huh? Here, when I gave you this solution, okay? And when I gave you this solution for non-vanishing epsilon, or when I went to the solution of the equation close to omega m tot equal 1. The only difference is that I have to add the unclustered component, which is rather trivial to do. Now, I just want to stress a few things here. Let us take first omega d constant. For omega d constant, you see that in the past, it's really quasi-constant, okay? In the past, it's quasi-constant. With small evolutions though, okay? And typically, with respect to Z, the slope is negative, exactly how I showed you in the first slides. It's slowly decreasing, okay? Remember, increasing omega m is increasing Z. Now, this is why you can choose the following strategy when you make the numerical integration. Here we are in the regime where both gamma and WDE, if you assume WDE is constant, are where they are both constant. So clearly, you must have the same asymptotic value for omega, omega minus infinity, as in the constant gamma case. So this is how you can actually integrate those equations mathematically. You choose these initial values. Now, choosing this initial value, you can calculate gamma as a function of omega m, And you can expand it in solutions, and you get this result, and you see that it's remarkably accurate. Already at first order, but you understand why. Because you see here, this part is really quasi-linear, okay? So it's no wonder that the first order is enough. Of course, when you have in mind observations, it's better to use the redshift. And when you do this expansion, you must remember that this is not a free parameter here, okay? This will be calculated numerically, but this is not a free parameter. It's all settled by the gamma naught, which is calculated, W naught, which is given by the model, and the omega m naught, which you choose. But you can see that it's accurate below the percent level up to Z of order 3. All these results are for constant W. But you can extend it even to smoothly varying dark energy models. But I will not discuss it. What I want to discuss now is this here. You see this here, this. I think this is probably lambda CDM here, okay? And you see, you might wonder, what happens here? Is this a numerical artifact, or is this an exact result? Actually, it's an exact result. When you look into the asymptotic future, you will see that gamma to leading order is given by this formula. In other words, gamma goes to gamma infinity. So this is what I just mentioned earlier. Even when you solve the exact equation and you don't assume gamma constant, gamma will tend to the same value as that which is obtained for a constant gamma, provided we have the same W at infinity. So I summarize it in this way, okay? The true gamma, its asymptotic value as a function of the asymptotic value of W is the same as the constant gamma when the W that I get with the constant gamma is equal to this W. So by W bar, I mean the W which is obtained as a formula for a constant gamma. So you take the constant gamma, which gives a W bar infinity, which is equal to this W infinity. So it's the same value as the true omega. So gamma tends to a constant value. But in which way? In a way that it diverges. And this is exactly what you see. So it's not an artifact, you see? It goes to a constant value. It's really a constant, okay? This is actually lambda CDM, and you see it's 0.666. It's the future value is 2/3. And you see it's straight because indeed, the derivative with respect to omega m diverges. The derivative with respect to z diverges too. But d gamma DLNA does not diverge. And I remember in the very early days of this work, I realized, without knowing what will happen in the future, I realized that if we allow gamma to evolve, it must evolve in such a way that this must tend to 0. Otherwise, W will diverge in the future. So what we do here, we can do in the past. And we get in the past in the same way that gamma tends to gamma infinity, gamma will tend to gamma minus infinity with the same speech as here, okay? So you understand now the notation. It's the same as here, but now it's for the past. Now, can we understand a bit more? Can we understand something about the slope of gamma? So for this, I will use the curve big gamma of omega m. And it's the curve which is defined in such a way that WDE is W bar. In other words, by definition, if I take a couple omega m, gamma of omega m, this here will play the role of the growth index in such a way that the growth in, that the equation of state that we obtain for this omega m is the true equation of state of dark energy for this given omega m. Okay? So I view W bar as a function, which it is, as a function of omega m and gamma, and no, this gamma is gamma of omega m. And the curve gamma will take, for a given omega m, that value of gamma. So the curve big gamma of omega m will take that value of the growth index, which for this omega m gives you WDE. So we have this by construction. And you remember that the true gamma tends to gamma infinity in the future, gamma minus infinity in the past, but these were also, this relation was also for a constant gamma, okay? So this is also for gamma naught. In other words, gamma naught is gamma infinity. Gamma 1 is gamma minus infinity. I mean, if I construct the true gamma between 0 and 1, they will meet with the big gamma of omega m in the future and in the past. Here you see it in a beautiful figure. There is a lot to explain here. This is for the gamma for lambda CDM. Okay? This is the gamma for lambda CDM. This is the big gamma. Now, by construction of this big gamma, by construction of this big gamma, when a true gamma crosses the big gamma, it does so when the derivative is 0. And you see here, all these are solutions of the equation which cross the big gamma with a 0 derivative. So, with a 0 derivative. This is point 1. Point 2, as I said you, the two curves meet in both ends. But you see also that this is monotonically decreasing. Now, clearly, this is the curve, big gamma, on which whenever small gamma crosses, it crosses with a 0 derivative. Okay? So this means that if the true gamma, the one that goes to 6/11 in the past crosses somewhere the big gamma, as the derivative is positive, it will go like that. It can never anymore reach this. In other words, gamma cannot cross big gamma, and not only that it cannot cross, this means that it stays in the domain with negative slope, and so we have a beautiful theorem, if you want, that the slope of gamma is monotonically decreasing. It cannot do otherwise. Now there is more to be said. What are those curves here? Well, those curves we usually don't see in the literature. Why? Because these are curves where even today you have a non-negligible decaying mode. And this is because you have still the decaying mode that the value of gamma today, let's say here, it's so different from this value. Typically, when people do numerical simulations, they find, of course, like we did and like many other people did long ago, you find these values. Why don't you find the other values? Because the decaying mode is completely, has vanished, okay? But if it would not vanish, you could get either of these curves. But there is another thing which is interesting. Even if you have a non-vanishing decaying mode today, ultimately it will vanish, okay? And you can show that for all those curves, the way f goes to 0 here is the same. And therefore, the gamma is the same. And this is exactly, you see it beautifully. They will all converge to the same value of gamma in the future. Now, how many time do I have left? How much time, sorry, do I have left?
Yeah, so David, we started a bit late. So yeah, you have about 5 minutes or so. And then we'll take some questions. Is that okay?
Maybe slightly more, maybe 6 minutes.
6 or 7, okay, or let's go with that then, okay.
Okay, very good, very good. So now I want to give you a very nice illustration of the formalism. And it's DGP, Dvali Gavadat Separati. Why? Because in this model, as people have shown long ago, both W and G are given as a function of omega n. But then it's wonderful, because then I can just take, voila, here it's written, I can just take this equation, literally, because this will be given as a function of omega m, okay? And here, the G will appear here, actually. You remember? Okay, maybe somebody will ask this question and then I will answer. In the expression that I gave you on my first slide or second slide, there was a G in blue. And I said to you, we start with GR. So G is 1, but if you're outside GR, it will be hidden here. But it's a function of omega m. This and this, so I can completely solve the equation. Okay? Now, in the future, it's 2/3 weak gravity. In the future, W is like lambda. So the background behaves like lambda CDM in the future. But weak gravity, in the past, W is -1/2, and G tends to 1. So in the past, it's GR. In the future, it's 2/3. So this is very amusing. You would expect that in the future, you get an anomalous behavior of gamma, and in the past, you get a regular behavior, like in GR, for DGP. Just the opposite takes place. Why? Because what is important when you compute the gamma at -infinity, you make the calculation, you get this result. So what is important is this quantity. So if you want to have the same result as in GR, this should be 0. But in DGP, this is 1/3. Okay? This is 1/3. As a consequence, gamma minus infinity in DGP is 11/6 and not 9/6. So if this was 0, with this value of W minus infinity, you would get 9/16. But actually you get 11/16. In the past, though you go to GR, but you go in a way which is not smooth enough. And in the future, well, in the future, G is 2/3. You can show that actually, in the same way, you remember that all those gamma go to the same value for the same reason. Exactly for the same reason, the fact that you have here a G that is weaker doesn't change anything in the way f goes to 0. In other words, gamma at infinity for DGP is the same as in GR. So a corollary of this is that G1, D1, G1, D0, okay? If you have this both fulfilled, then you get the same result in modified gravity and in GR. So this is just interesting because you see, this was your question that you asked and my answer about limits. Of course, mathematically, it's the limit that is this value 11/16. But actually, you see, as a function of Z, it's very, this is DGP. It's very rapidly attained. Around, around 3. It's already attained, okay? Here you see, for illustration, lambda CDM, and you see that both curves meet indeed in the future. And this is this is the G. Okay, this is the G, which is 1. You should look at that scale. It's 1 in the past, 1/2. What was in the future? It was 2/3, sorry. 2/3. Okay? And you see both full curves, the blue and the other one, they tend to the same value as in lambda CDM. So this is beautiful, this analysis. Now, I leave this for you, and I will conclude my talk here. Thank you very much for your attention.
Okay, thanks very much, David, for a very interesting and thorough talk. I guess we're now open for questions and comments. It may be difficult to do in the seminar room.
Hello.
Hello.
May I ask a question? Your theory and this model is very interesting, but may I ask what's your motivation to build up this kind of equation of state?
Which one?
What's the motivation you want to build up this kind of equation of state?
No. Well, you mean this here? Or you mean in general?
Maybe the second part constrains gamma inside the GR. This part.
Inside GR? Well, I think you have in mind this maybe. So, again, I can constrain, I can show that the gamma is, that the growth index has a slope, so it's monotonically decreasing, but depending on the big gamma that you find, of course. Okay? You see that here, this is why it's interesting. This is why we give you this illustration. You see that the big gamma is not monotonically decreasing. And actually, you see what happens. It starts with a value larger than the asymptotic value. So the asymptotic value in the past is larger than the asymptotic value in the future. So it should decrease, for sure, it must decrease. But you see here, it decreases so much that it comes below. So the only way it can go up again is to cross again the curve big gamma. Now, this is an illustration, of course. If you want to constrain, if you want to give constraint on the slope of dark energy models, you have to compute the big gamma. So I don't claim to have a very general rule. Okay?
Okay, okay.
So I don't know if I answered your question, actually.
Another question is this gamma you gave here. May I ask this gamma, does this gamma will have some relationship with some observation parameter?
This one?
Yes, and the last page, the small gamma.
Oh, no, but the small gamma for sure. The small gamma will be a key target of big, though this talk is quite on the mathematical aspects of the gamma, okay?
I see.
The precise value of gamma, what will be the precise value of gamma, okay? The precise value of gamma, it's here, will be a key target of future observations. And actually, if you want, a key point is the following. Will observations find gamma close to 0.55? Or will it be very different? Because actually, there is a lot of things that I didn't say here, but in FR models, I didn't show it here. In FR model, gamma can be as low as 0.4, okay? With a big slope. So to answer your question, yes, gamma is important from the point of view of observations. And yes, it is a key target for future observations. And the main motivation will be whether we find a gamma close to 0.55 or not.
Thank you.
So David, this is sort of related to what you just said there. So we had a talk recently by Harry Desmond, and he's looking at warps in galaxies to basically constrain G effective. And he seems to get very strong constraints on like G effective deviating from G Newton. So they're pretty tight constraints. I'm just wondering which one you think will be more useful. Like, can you relate your gamma? Maybe it is related to delta G Newton, right?
Well, no, you're absolutely right that you can, of course, you can constrain G effective. Well, basically, G effective affect the growth of perturbations, and then you can imagine all kind of quantities which enter this anomalous growth of perturbations, if you see what I mean.
Mm-hmm.
So gamma is only one of them.
Okay, okay.
But I can imagine, okay, I have to think about it. But I can imagine.
So at the moment, Harry Desmond is claiming constraints like G effective is, well, delta G, he's claiming that it's less than or equal to 10 to the minus 4. At least at very low Z, like say Z less than 0.05.
Yeah, but no, but this is, I think you mean something else. This is I think you mean, he meant, or you mean the value of G effective today.
Yeah, that's what something close to
it. This I can imagine, but of course, it's not the only thing. You see, it's an interesting point that you raise.
I mean, you could essentially constrain modified gravities today or close to today, right? But maybe you want to go further.
Yeah, yeah. Take this example. Very simple. Masses scalar tensor. And masses just means that basically there is no mass term here. The derivatives are such, it's like you have no potential, basically. Okay. Then you see G effective today is G. It's not exactly G because you have this omega Brunzicki today. You see what I mean?
Yeah. So you just make it to be a large parameter and then you're done.
Yeah. However,
but then you need to explain why that's a large parameter, right? Today.
Yeah. And no, but I just give you a theory when we know, where we know that G effective today, okay, must be extremely close to G.
Okay.
And will be extremely close to G.
Yeah, but then you can ask, is W Brand sticky? I mean, is it reasonable? It's could you get it from some fundamental theory or?
No, but here this we get from scratch. But the point is, and this was my point, it's today.
Yeah.
If you go into the past, it can deviate. And if it deviates, well, you will affect the growth of perturbations. And if you affect the growth of perturbations, I insist that the point is not, when we say that gamma is different from 0.55, it's not just, you see, remember this, figure here. Actually, you will get big slopes also, okay? You will also get big slopes. So when I say that it let me go back here for this theory, okay? While this is one, so G effective today over G is one. In the past, it will not be so. And so gamma can deviate a lot. It can have large slopes.
Okay, yeah.
You are right that you should look at two things. Actually, three things. The value of gamma today, the slope of gamma today, and the dependence on scales.
Okay. And can I ask how optimistic you are that we can actually determine these things observationally? Particularly slopes in general are very difficult to determine.
Absolutely, I don't know. But you know, I remember the days when people said that it will be, you are too young for knowing those days. Where people said it will be impossible to get the anisotropies of the microwave background because they are just too small, well, which is true. They are fantastically small and they are fantastically far. And people did it. So maybe it's possible, but I'm not an expert in that, okay?
Okay.
But you're perfectly right. Whenever a slope is involved, it's a problem. Okay. And the same is scale dependence, by the way. It's not easy either.
Okay, thanks, David. Any other questions, Stephen? Okay, and nobody online? So if we've no more questions, then I think we can thank David for a very nice talk. Thank you, David.
Okay, thanks to you. Bye-bye, good night. No, good day. Good day.
Good night. Take care, bye-bye.
Okay, bye-bye.